Hi, and welcome to this look at another applied electrode potential and equilibria exam question. So this one is a bit more obscure, so we need to process and think about what we're being asked first before we try and start it. So it's the tail end of a longer question, so it obviously says the student modifies the experiment in part A. So we're not interested in part A particularly, but what we are interested in is the steps that the student is going to take this time. So you can see that step 1 says add excess zinc to a 250 centimeter cube sample of river water and warm gently. Now this is obviously taking the chemistry to an outside the lab type of setting. So a sample of river water was taken outside and then some excess zinc is added to that back in the lab and it's warmed gently. And we need to try and think about how that's relevant to the redox system information that we've got in front of us. Now normally you get tables like this in questions where they tell you explain the observations in terms of equilibria and electrode potentials. You can see at the bottom it says use the information in the table above to explain the reasons for step 1 and for step 2. So it doesn't necessarily direct us explicitly to use the half equations or the electrode potentials or the idea of equilibria. But we can do that to actually explain what we're doing here. So we need to find where zinc is in the table. So it's in redox system 1, and I've circled it, so it's obviously going to be proceeding from right to left. So the equilibrium position is going to shift from right to left. And in doing so, it's obviously going to lose electrons. You can see that it's losing electrons as it moves from right to left, as it turns into Zn2+. So the first thing to do is to spot that it's acting as a reducing agent, because if it's losing electrons, that means something else must gain them. And we can make a comment about the more negative electrode potential value than redox system 2. Now redox system 2 contains the iron species, iron 3+ and iron 2+, and those are what are mentioned a bit further up. So there's a connection being made between those two. So this one has an electrode potential value of plus 0.77 volts. So obviously the Fe3+ is being reduced to Fe2+, being the more positive out of the two electrode potentials. The position of equilibrium is going to shift to the right. And then finally, we need to think about step 2, where it doesn't make any particular mention of delta H or any enthalpy considerations, but it does say cool the solution and remove the excess zinc by filtration. There's a more subtle thing to spot here. Step 3, which you're not explicitly directed towards, says acidify 25 centimeter cube portions of the filtrate from step 2, then titrate each portion with 0.0025 moles per decimeter cubed potassium manganate 7. Now, the implication there is you're really using the potassium manganate 7 to oxidize iron 2 to iron 3. So you want these two half equations to be working in conjunction with each other. Now, the problem we have is if zinc is present, then because the electrode potential is more negative than plus 1.51, and also the electrode potential of our desired reduction is plus 0.77, then what would happen is either of these two things could potentially react with MnO4. So essentially, removing the zinc in step 2 prevents the potential oxidation of it by the manganate, which is being used to oxidize Fe2+ in step 3 instead. So coming back to the idea of using equilibria and electrode potentials in your wording. Equilibrium shifts explain in simple terms which way each redox system proceeds, to the left or to the right, and electrode potentials will justify this in terms of more negative proceeding as oxidation or vice versa. So now we've done a bit of thinking about it, let's look at how we could construct our answer in the answer space provided. So like we said, zinc is behaving as a reducing agent. The electrode potential for redox system 1 is more negative than that for redox system 2. Therefore, the position of equilibrium for redox system 1 shifts to the left, and the position of equilibrium for redox system 2 shifts the other way. If zinc was still present, the manganate 7 would oxidize it. We don't want it to do that, so therefore, because we want step 3 to be what we actually see, rather than it inadvertently oxidizing the zinc, we get rid of the zinc by filtering it out of the reaction mixture. So quickly checking the mark scheme to see what ways we could have got our marks. So let's have a look at where the marks are awarded. And I'm going to color code them according to marks that are awarded for different approaches. In other words, you can get it in different ways, and marks that have to actually be awarded based on what the mark scheme says. So the marks that are in orange, they're required because they use the information in the table as the question directed you to do. The ones that are highlighted in blue are alternative ways in which the same idea can be conveyed to the examiners. So for example, you can see that in the ones that are highlighted in blue, there's an equilibrium argument, there's a redox argument, or you can just use the equation. So any of those approaches are fine. And that comes back to the fact that the question didn't say to us, explain in terms of equilibria and electrode potential. So that means the mark scheme has to reflect that by being more flexible in the approaches that are allowed by candidates. Okay, thanks for listening, and I hope this has been useful. Until next time, see you soon.